And now we are passing to the second part of the character animation. We saw how to deform the skin of the character, and the question is how can we control the motion of the skeleton? And first we need to represent the skeleton. Usually it's common to represent it as a hierarchy for articulated character. All children therefore follow the transformation of the parent, and we need to define a root node, usually positioned at the hip of the character. The skeleton is a tree, so any joint can have multiple children, but it can have only one parent. It's also convenient to express the transformation usually relative to the parent and not necessarily in global coordinate. For instance, it's easier to express the orientation and position of the ankle with respect to the knee rather than in some arbitrary coordinate system. So the first thing we usually need to do is to convert these local coordinates to the global frame in order to perform computation in the same coordinate system. If we have our rigid transform expressed in the 4x4 matrix form, then we can say that the matrix adjoint A in global coordinate is the matrix of the parent expressed in the global coordinate times the current matrix of the current join expressed in local coordinate. And if we have an explicit representation with translation and rotation, then we can say that the current rotation in global coordinates is the rotation of the parent in global coordinates times the current rotation in local coordinate. And the current translation in global coordinate is the translation of the parent in global coordinate plus the rotation of the parent in global coordinate applied to the current translation in the local coordinate. And here is an example of a very minimalistic way to encode the skeleton data, only limiting ourselves to contiguous structure in memory. We can encode the geometry as a buffer of rigid transform, either as matrices or as quaternion translation. And the connectivity of the skeleton tree is stored as a buffer where the entry I stores the index of the parent of I. And by convention, we can consider that the parent of the root node is -1, for instance, and then we can continue after that. The only constraint is to define the geometry of a join after its parent in the buffer. And here is an example of C++-like code converting the local coordinates to the global one using this structure. Now, when we want to animate our skeleton, there is two main strategies. The first one is called forward kinematics, or FK in short. Forward kinematics is simply the action of setting the join orientation manually for each join, and then interpolate the rotation of each join using standard interpolation and animation curve. One of the advantages of this approach is that it automatically generates curved trajectory of the end effectors, like the hands, and this is rather a natural type of motion. But forward kinematic isn't always adapted in all situations. It's fine when we move our hand in the air, for instance, without constraint. But when we have contacts, like for the feet during a walking motion, then the extremity of the character should remain in contact or sometimes fixed during the animation. And controlling the position of the extremity of a character in setting the angles at the articulation is, however, not an easy task to do manually. And actually, automatizing this process is called the inverse kinematics. So inverse kinematics, or IK, is the way where we can describe an objective position and orientation to an end effector, which is an extremity, and compute the angles of the intermediate joints from the root to this end effector, such that this constraint is satisfied. So if we have an IK solver, this seems very interesting, and we could think that all characters are fully handled using IK. But actually, if you look how artists work, you will notice that now both forward kinematics and inverse kinematics are used in the generation of animation. One of the reasons is that when you interpolate between IK motion, then you will have more easily straight trajectories. And natural motion is never straight. Having straight motion looks robotic, and artists try to avoid them. So in general, free motion in the air are often handled using forward kinematics, while constrained members happening during contact are handled using inverse kinematics. And standard modeling softwares offer both parametrization. Also, one thing we can note is that IK is a complex problem actually. In the general sense, we have a position pk as a function f of several angles theta I, or rotation in 3D, and we try to find the theta I as the inverse of this function f. Let us look at the simplest possible IK problem, one target along a chain of two bones. Then we can actually compute the closed form solution for the angle θ1 and θ2 with respect to the coordinates of the target x, y, which is valid when the distance of the target to the base is less than L1 plus L2. And we can see that this function, f inverse, is complex. It's highly nonlinear, and there is no closed solution for an arbitrary topology of bones in general. Also, there may exist multiple solutions. Even in the simplest case, we have already two solutions bending up or down. And these two solutions are discontinuous. We cannot go from one to the other while preserving the constraint. So inverse kinematics in general has to be solved numerically in most situations. One way to tackle the nonlinear problem is to use linearization. So we consider the skeleton to be in an initial configuration, and we are looking for a small displacement of the target P going to P plus dP, and associated to a small change of angle theta going to theta plus delta theta. In this case, we can consider the linear approximation of f along small variation, and we have the relation that delta p is equal to the Jacobian of f times delta theta. And the Jacobian is the partial derivative of f with respect to theta. So we would like to solve the problem in saying that delta theta is the inverse of the Jacobian times delta p, but actually the Jacobian matrix is not square. There is usually much more unknown than constraints. So in most situations, there is multiple solutions. To find a numerical solution, one can use in such case the pseudo-inverse of the Jacobian matrix. So the pseudo-inverse is called J+, and is given by the product J transpose times J transpose inverse. By construction, J times J transpose is a square matrix, and J times J plus is equals to identity. So J plus can play the role of some kind of inverse matrix in a more general sense for non-square matrix. And in this case, we can write that delta theta is equals to J plus times delta p. The pseudo-inverse can also be computed using the singular value decomposition, with J plus is equals to V times sigma plus times U transpose, where V, sigma, and U are coming from the singular value decomposition, and sigma plus is the diagonal matrix containing the inverse of all the non-zero singular values and zero otherwise. Of course, the pseudo-inverse only gives one solution among multiple ones, and there is a subspace of possible solutions. So there is a range of methods that tries to use this freedom to find specific solutions that limit instabilities in adding some type of damping, for instance. Also, finally, we can use Newton methods, for instance, to inverse numerically the function f. And to get more information about the numerous possible approaches, you can find a state-of-the-art on the inverse kinematic approach from 2017. Beyond numerical approaches that can sometimes be computationally costly, there is also the possibility to use heuristic and more geometric-based approaches. One of them is the cyclic coordinate descent, or CCD. The idea is to iterate on some rotation around each bone to be as close as possible from the target at each step. So let us see how it works on this example with 3 bones and the target shown in red. First, we start with bone 3. We rotate it so that the end effector is the closest to the target, meaning that the bone is actually aligned with the target. Then we rotate bone 2, and in this case we set the end effector, the second joint and the target to be aligned. And then we do the same for the first joint and rotate it such that the target and the extremity and the joint are aligned. And then we restart from bone 3 and so on until convergence. Another heuristic approach is the one called fabric. In this case, there is 2 iteration direction. First, we start from the end effector. We take the last position P4 and force it to be at the target position T. In moving P4, we have changed the bone 3 in direction but also in length. As the bones have constant length, we bring back P3 into a new position P3 prime along this new bone direction, but such that the distance P4 prime P3 prime is the original one, D3. Then in doing that, we modify the bone 2, and to correct for the change of this length, we bring the position P2 to P2 prime along this new bone direction and with the correct length. And we iterate similarly with the first bone, which then modify the root position at last. So at the end of this first iteration step, we have a correct extremity position, all the lengths are preserved, but the root is now at a wrong position. So we restart the algorithm, but working from the opposite direction. So we force the first position now to go to the initial one, which therefore impact the second bone, so we modify the position P2 prime into P2 prime prime in order to preserve the length of the bone, and so on until reaching the extremity. And we can iterate like that once in forward direction, once in backward direction, until converging. So these heuristic approaches have the advantage of providing fast results. They don't need to solve systems of equations, but they, however, do not guarantee to find the result, and they can be associated to sudden change of position and orientation during the motion. The angle found by the approaches are also not necessarily compatible with what we can expect from a plausible character. Therefore, for actual humanoid character, more constraints such as limitation on maximal angles have to be added. Now we are going to see different methods to synthesize and control the animation of the skeleton. And one of the most simple ways to generate a complex animation is to pre-store several animations that can loop, like a walking motion, running motion, or a static pose. And then if we want to go from one motion to the other, then we create a translation in blending the skeleton animation. And this is what we see here when varying the weights of blending from one type of animation to the other. This approach works for any stored animation, but it has 2 limitations. First, the blending is not instantaneous, and it can take some time to be performed. This can be a limitation, especially in video games, where the motion have to be very reactive when the user presses the action button. And this was a problem in the first video games using realistic motion, typically recorded using motion capture, that were having a delay before starting as if they were requiring long transition to be run. And second, if we use linear interpolation, we may generate bad or incoherent poses of the character, as a blending between different postures may not look natural. One of the most common approaches to tackle this issue in video game is the use of motion graphs, also called move trees. An animation character in video game is often associated to a lot of possible motion, often stored as small sequences. For instance, it can have a sequence of punch, of dance, of jump, and so on. And these sequences can be designed manually or obtained from motion capture. Passing from a sequence to another is actually feasible without visible artifact if some poses between the 2 sequences are close to each other. And 2 sequences can actually allow seamless jumps at different frames of their sequences. then the motion graph is actually the graph storing the frames where a jump is possible between the different sequences without visual artifact. Therefore, at the runtime, when the user asks to move from a sequence to another, the actual change of animation is performed at the first possible jump that is allowed. This ensures that the change of animation remains coherent and is often faster than doing a blending between motions. Of course, in practice, these motion graphs can be very large, and computing and storing such optimal transition on a large set of motion can be a challenge in itself. Pre-recorded motion and motion graphs allow reactive character and are standard in video games, but their use remain limited to predefined motions. A character only using predefined motion has therefore limited realism in situations where its recording motion hasn't been prepared for it. For instance, how should a character react when he meets an obstacle? Should he fall or not? So if you want to go toward more autonomous reaction of the character with respect to its environment, then we usually have to integrate a simulation of the behavior of the character. However, fully simulating an entire human is very challenging as the number of muscle and parameters involved would be very high, and this is out of reach of real-time application. A common idea is to mix between predefined motion and modify them with some level of physics in order to allow some user perturbations. And the main approach for doing that is the use of the so-called controller. First, the predefined motion, such as walking motion, are split into sequences of sub-objectives, like left foot on the floor, then move up the right foot, move it down, touch the floor, and so on. So these sequences are organized as a state machine. When we reach one state, we aim at the next one. And this sequence gives the gate model. This model is actually described at a given time t by a set of angles, theta target, and angular velocity, theta target prime. On the side of this objective gate, we have the current pose of the model that we call theta and theta prime. In the ideal situation, without obstacle, theta and theta prime are equals to theta target and theta target prime. But the user or the environment adds some perturbation. This perturbation acts as constraint on the position of the character, and therefore they can be expressed as some modification on the current angle and velocity of the joint. We call this perturbation delta theta and delta theta prime, and we add this perturbation to the current pose. The controller step is actually taking place on each joint and take as input the current pose of each joint and the target one, and compute an error measure out of it. This error is inspired from proportional derivative controller in automatics, and compute alpha times the difference of angles plus beta times the difference of the angular velocity. And this error is interpreted as a correcting force, or more precisely a torque, that should be applied to the joint. Then the next step is to feed this torque to a physically based simulation, which is usually a rigid body simulator, that will integrate the pose of the model from time t to time t plus delta t, and taking into account the gravity and the torque from the controller, as well as external constraints. The output of the simulation is a new set of orientation and velocity of the joints at the next time step, and then we loop back to take into account the new perturbation and gate objective at this next time step, and so on. This approach allows to model character that self-adapts to the external perturbation. It has physical response like falling when losing its equilibrium thanks to the simulation, while trying to reach its objective target gate when no perturbation are applied. One of the hardest parts of setting such approach is to correctly fit the values of the controllers, alpha and beta, that needs to be adapted for each joint and that depends on the morphology of the character. There has been multiple ways to fit at best this value, ranging from manual set to learning approach and optimization with respect to some high-level objective functions. And now I will briefly end in presenting some other approaches to give you an idea of several possibilities, but without going into the details. Of course, you are not expected to go into details of all of these approaches. So another type of approach is motion transfer. The idea is to try to find a mapping from a given motion set to a specific character to another one with a different morphology. One of the famous examples of the use of motion transfer on different morphology is the game Spore, where the motion of the limbs is encoded in some local coordinates, typically relative to the length of the bone, the position of the ground, or the position of a target. And then, when a new hand or a modified one is added to the creature, the local motion of a limb that has a specific function, like walking, grasping, and so on, is mapped back in the global coordinate system. Local coordinates are very efficient and simple to set up, but of course their use could lead to self-intersection, for instance, if the morphology drastically changes. Then some more recent approaches have proposed solutions that first map the new skeleton motion and then take into account the surface of the shape, in inflating the surface when the character becomes more and more fat and solving for collision in the process. Other approaches focus on interactive design of the skeleton trajectory. And a successful approach of these recent years is the use of the so-called line of action, which is a kind of a medial curve typically drawn by artists to give the general pose of the character. Here the user can draw this line and the character will automatically try to match at best this medial line. We can extend this idea for space-time trajectories, where the user can sketch a curve which is interpreted as both the alignment of the pose and the trajectory of the shape. And iteratively, we can refine the detail with new sketches. And recently, this type of trajectory sketching have been proposed to finally adapt character limbs motion displayed as trajectory in either spatial coordinates or view as a function of time, and that the user can directly edit. And finally, we have the automatic synthesis of skeleton animation. The seminal work on this aspect was proposed by Carl Sims at SIGGRAPH 94. In this work, evolving virtual creature. If you remember, Carl Sims was a researcher and artist who also proposed some early particle system animation. These creatures were made of pieces of rigid bodies that interact with the environment using a simulator, and the motion sequence activating the muscle is found in optimizing an objective function, like reaching some goal first or moving as far as possible. Note that at that time, reproducing these results were very hard due to the limitation of the computational power. Now, thanks to the widely available computational power, these approaches are more easy to set up. The main method to generate such autonomous creature is via the use of reinforcement learning, where you have a simulated model of your character composed of a set of pieces linked by muscle actuators. And the optimal sequence is found via lots of trial and errors, trying to reach an optimal score from a specific objective function. The fitting of the optimal parameter can be done, for instance, on the value of the controllers on the joint. Deep reinforcement learning can also be used when there is a lot of degrees of freedom. It was used, for instance, in 2017 to generate creatures that can learn by themselves to fly by flapping their wings in a simulated fluid environment. When simulation is too complex or not available, brute force deep learning can also be used, and were proposed in 2017 for character animation in the context of video game. In this case, a large database of motion capture were recorded, and then learning was performed to find the best transition between all the possible motion cycles depending on the position of the terrain. Of course, these approaches are limited to the capability to learn on a sufficiently large and adapted database of motion.